Initial Value Theorem, an explanation and few examples. Question is, if you only know the Laplace transform x of s of a time domain function x of t, how can you find the initial value of this time domain function x of t at time t equal to 0 without requiring to find the x of t function first? So let's first illustrate this via an example. So consider this example. Let's say that S-domain function that is available for this example is, so you're given x of s is s plus 1 over s plus 2. So let's say this is the Laplace transform of a time domain function. Traditionally speaking, what you would do, forgetting about initial value theorem, would be, alright, if I want the initial value of time domain function, I have to figure out the time domain function. So the best way to go through the process of inverse Laplace transform would be first dealing with a partial fraction expansion, so using partial fraction expansion. So I'm just trying to illustrate why we need this initial value theorem, how it can be useful. So using partial fraction expansion, you would say, okay, this x of s is also equal to 0.5 over s plus 0.5 over s plus 2. You can easily see that this is exactly equal to what is written here. Okay, with that in mind, now you can actually use the inverse Laplace transform, and because the partial expansion resulted here are just the Laplace transform of simple functions. In this case, x of t is this guy here is well known to be just 0.5 ut, and ut is the unit step function, and the other one, this guy here, is just a simple exponential 0.5 e to the minus 2t ut. Ut is just unit step function. As you know, ut is just as simple as 1 for t greater than 0 and 0 for t less than 0. You can also assign it for equals 0. Okay, so with this in mind, now things are easy, because you would say, okay, so let me just further simplify this. It's 0.5, 1 plus e to the minus 2t times ut. Alright, now with this function, what I need to do is I would say, okay, this is my function, so I can simply say, then x of t equal to 0, which is the initial value, is just simply obtained by substituting 0 here. E to the 0 becomes 1, then 1 plus 1 is 2, and 2 times 0.5 is 0.5 times 2 is just 1. Okay, so in this case we are lucky because it's a very simple example. Generally speaking, it can be extremely difficult and time-consuming to figure out the inverse Laplace transform just for the purpose of figuring out time domain function in order to get the initial value. If we have a much more complicated x-domain function, this would not be straightforward. So what we want to do is figuring out the value of initial value just from the given s-domain Laplace transform, not requiring to figure out the time domain function first. So here is the initial value theorem. Okay, so assuming that the Laplace transform of x of t and also the Laplace transform of derivative of x with respect to t both exist. Okay. And Also, the order, and also for x of s, which is this guy, the Laplace transform of x of t. For x of s, the order of numerator is less than the order of denominator. Okay, so with this, then we can show limit of s x of s when s goes to infinity is actually equal to x of 0, which is basically x at time equal to 0, which we are referring to as initial value. So it means to find initial value, you just need to simply compute limit of s times x of s when s goes to infinity. No need to figure out the time domain function directly. But we need to be careful. This initial value theorem is only valid, can be used, if these conditions listed here are satisfied. Okay, so let's first prove it. It's easy. So let's say b is the Laplace transform of derivative of function t with respect to time. So in this case, we would say, okay, by the definition of Laplace transform, it's as easy as saying it's integral from 0 negative to infinity dx with respect to time, and then e to the minus st dt. Okay, and this is obviously equal to integral from 0 minus to infinity e to the minus st, just change of argument of integral, so it would be dx over dt times dt is just dx. I'm not changing this thing, but remember we're talking about time equal to 0 negative to time equal to infinity. That is still the case here. Okay. Now keep this in mind. This is equal to b. The thing is, when we are computing limit of b, which is this, s goes to infinity, the argument, the function inside the integral goes to 0 because s is going to infinity. So as a result of that, you're talking about just limit of integral s goes to infinity e to the minus st d of x, which is 0. Okay, so this is what I need. Let's say equation 1. Now let's also at the same time compute this or further simplify this guy. So I can use a well-known equality for integral, and I can rewrite this guy in the form of x of t e to the minus st from 0 negative to infinity minus integral from 0 minus to infinity x of t derivative of e to the minus st. Okay, so in this scenario, assuming the function is bounded in time, then at time infinity this component is dominant, it goes to 0, it will kill everything. The only thing remains from this portion is just negative x of 0 negative, and this side derivative of e to the minus st becomes plus s times e to the minus st because it's multiplied by this guy, so we get plus s times integral from 0 minus to infinity x of t e to the minus st dt. Alright, this is well known. That is just the Laplace transform of x of t. Okay, basically just x of s. So final outcome is we're talking about negative x 0 minus plus s times x of s. Okay. Alright, so b is also equal to that. Alright, so from 1 and 2, what we can say is limit of this side, which is equal to, should be equal to that side. So limit of b when s goes to infinity is equal to taking from second equation limit of s times x of s minus x. This is, by the way, time domain function. Be extremely careful about this. This is Laplace transform s domain function. So 0 at time, x at time 0 negative, when s goes to infinity is equal to, from 1, so this is from 2 and this is from 1, 0. Okay, taking this side, we get limit of s times x of s when s goes to infinity is just x of at time 0 minus. Now the thing is, since in s domain representation of function x of s, since x of s you're saying is in the form of a numerator, okay, and a denominator, okay, and you're saying the order of numerator according to the requirement is less than the order of denominator. So you're saying numerator is in the form of, for example, s, whatever coefficient you want to apply to it. So let's say a sub m s to the power m plus a sub m minus 1 s to the m minus 1 plus, and so on, plus a1 s1 plus a0. So let's say that's numerator. And you're saying denominator is an sn plus an minus 1 sn minus 1 plus, let's say, let's name them b to avoid any confusion, b1s plus b0. So we are saying, according to the initial requirement that is written here, we are saying m, the order of the numerator, should be less than n. With that condition, when s goes to infinity, this thing goes to 0. This guarantees that this requirement over here, this portion, it guarantees that, so this requirement, it guarantees that there is no discontinuity at time 0 for the time domain function x of t. So this guarantees that x of 0 minus is equal to x of 0 plus. There is no delta t, there is no Dirac discontinuity at time 0. So that's why I can simply just say, because of that requirement, effectively I'm saying x of 0 plus as well. X of 0, basically, there is no discontinuity. So let's try it then. So back to example. Okay, back to example 1. Let's try. So we are saying, according to initial value theorem, x of time t0 should be equal to limit of s, x of s, when s goes to infinity. Okay, so x of s is given here. So it becomes multiply s by s plus 1 divide by s plus 2 limit when s goes to infinity. These two s cancel out, and when s goes to infinity, this obviously goes to 1, and that is exactly equal to the time domain function that we figured out at the beginning using a straightforward brute force approach of first computing the time domain function and from there figuring out the initial value. Reason we can do it, because for this x of s given to you, it satisfies these requirements. Basically, both Laplace transform and derivative, Laplace of derivative of the function both exist. At the same time, the order of numerator here is 1, while the order of denominator is 2. So it satisfies the second requirement as well. Another example, just be careful. Sometimes initial value theorem holds, while you cannot apply final value theorem. For example, let's say in the second example, you're given x of s equal to 1 over s minus 2. Okay, so the problem with this function is if you use the brute force approach to figure out the time domain equivalent corresponding to this Laplace transform. The function is not bounded because x of t contains a component of e to the plus 2t, which goes to infinity as t goes to infinity. So while the final value in time domain for that function is meaningless, but initial value can still work because this function satisfies this requirement. The order of numerator is less than the order of denominator. So in this case, x of t equal to 0 is, according to this, is just limit of s times 1 over s minus 2 as s goes to infinity. So it becomes 0. Basically, this function at time 0 has a value of 0, and you can actually see, if you want to double check, the time domain equivalent of this second example function is 0.5 e to the 2t minus 1 ut. So in that case, you can see that at time 0, this component is 1, 1 minus 1 is 0, x of 0 becomes 0. Alright, hopefully this is helpful with respect to how to use initial value theorem. There was an earlier video that I posted and covered the final value theorem.